All right. All right. Thanks everyone for joining. This is taught on focused mostly on ICESat-2 in altimetry. So ICESat-2 is a freaking laser.
Lasers.
Yes, lasers. Okay. Oops. All right. So altimetry, for those that may not be familiar, I think most people are, but just for the record, it's basically measuring how tall things are. It's measuring elevation. And so, oops, that's the essence of it for satellites. This is like kind of the basic, the altimeter range. That's a radar there, but I'll get into it in a moment. But that's basically the height. And it's in concept, it's really quite simple. It just you send down a signal. That signal hits the surface and bounces back. We know that signal is going at the speed of light. And so if we time the difference between when it left and when it came back, that's the round trip. You can calculate the round trip distance, get the divided by 2, and you get the distance there. Everything's done relative to reference ellipsoid. There's a lot of other things going on, but basically you're just bouncing it off the surface and timing it. There's been a lot of satellite altimeters over the years. This is not a complete list, although I picked out the ones that I thought were of particular interest as background. The very first one was actually on Skylab. They put it on the space station, the mid 1970s space station. It had just a little bit under a meter accuracy, which in some senses doesn't seem too bad, but it's not great for trying to measure like a geophysical parameter on Earth. Then there was the GEOS, which was launched at about 40 centimeter accuracy, better, definitely, but still not great. And then CSAT is really, I think, in terms of altimeters, the first one that really got to the point, had enough accuracy that you could really start doing something with it. So it's called the first scientifically successful altimeter. It could basically measure like ocean surface height and get sea level to some degree of accuracy. It didn't last very long. It only lasted 4 months or so. And it failed officially. The official word is that it failed due to a massive short circuit in the electrical system. However, there is a conspiracy theory out there apparently that when they started looking at the data, they realized that they could see submarines under the ocean surface, and the military shut it down. And this is the cover story. So, if you want a good conspiracy theory, CIA, military, killing JFK, whatever, and covering up altimetry data. But it did show, even though it was short record, it showed that ocean height could be accurately measured from space. So that led to eventually the Topex Poseidon mission, which is a NASA CNES, which is the French space agency. Forget what that actually stands for. And that launched in August of 1992. A really successful mission. It lasted 13 years, got down to 4 centimeter accuracy, and is really kind of the start for ocean remote sensing. Sort of the altimetry climate record really now. And then that was succeeded by Jason satellites. There's been 3 of those starting in December 2001. Got a little bit more accuracy. Oh, there we go, Marianne. Thank you. Good. Marianne would be the one that would know that. And then more recently, the Sentinel 6 altimeters. Sentinel 6A was launched. Their Sentinel 6B is due to be launched by the information I found, which may not be totally accurate, but it's just in like 9 days from now, it's going to be launched. And Sentinel 6A was named after Michael Freilich. Folks who have been around a while may recognize that name. He was at NASA, he was the NASA Director of Earth Science for several years, 13 years or so. He sadly passed away in 2020, not long before the launch, actually. So it was named in his honor. And then there's the SWOT, Surface Water Ocean Topography, which is also a NASA CNES. Actually, I think NOAA was part of this as well. And that's been operating. And the thing with SWAT that's different than these others is that it's actually looking also at inland waters, rivers and lakes, not just the ocean surface. So it has a higher resolution. The accuracy is not quite as good over the inland waters, but still good enough to get good data from. So these are all what's called radar altimeters, which I'll talk about in a moment, and they're focused on the ocean. Just wanted to show an example. This is a little bit on a tangent, but I thought this was fun to show. This is sea level, starting with Topex Poseidon, and going through all the Jasons and now the Sentinel 6. And you can see, there's variability, but there's a pretty inexorable rise and consistent rise in sea level. This is actually done at the Colorado Center for Astrodynamic Research, which is in the aerospace engineering department, which is where I actually got my PhD from. So I did a little bit of work on early Topex Poseidon, or even before Topex Poseidon, at the start of my grad school career. So it's kind of neat to see this going. I then went on to more interesting things, frozen waters instead of liquid waters. But one of the things you see here on the right, there's the sea level change, but it stops short of the polar oceans pretty much. And it's got about a 66-degree latitude limit. So these altimeters were focused on the largest part of the ocean, but they basically did not cover and do not cover the polar regions. And so they're not really useful for that. So what about the cryosphere? Well, as far as radar altimeters go, ICESat-2 has been a really great success. That was launched in 2010. It's a radar altimeter. So it's using radar, which is microwave pulses, and measuring the distance. It's got roughly 250-meter spatial resolution. There's CryoSat-2. You're like, where's CryoSat-1? I believe it's at the bottom of the Barents Sea or somewhere in that area. Unfortunately, it failed to launch in 2005. But it's really great. ESA, the European Space Agency, kind of jumped on this, and despite the failure, they were able to build another one relatively quickly. It still took 5 years to launch, but they were able to get that up, and it's been working for over 15 years now. And there is Crystal, which is Copernicus Polar Ice and Snow Topography Altimeter, which has a plan, at least right now, 2028 launch. That's always iffy and things get delayed. I think it was originally 2027, so it slipped some. But that's the idea, is that will carry on and continue CryoSat-2. So the hope is CryoSat-2 can keep operating until then. So now LiDAR and laser altimetry. So these have all been radar altimeters, sending out microwave signals. LiDAR is light, visible light. Light detection and radar stands for. LiDAR has a lot of different applications, and there's different ways of using LiDAR. Altimetry is one of those, one of the main ones, and that's what I'm going to focus on here. It's basically using lasers to reflect off the surface and estimating elevation, as opposed to like profiling or other things that LiDAR can be used for. So in terms of laser versus radar altimeters, radar has certain advantages. Number one, it sees through clouds and other atmospheric effects like aerosols. You don't have to really worry too much about the atmosphere as far as getting a signal. It also can penetrate through some surfaces, which can be useful if you want to get a more direct measurement of something that's covered with like snow or dust. And so that can be helpful for that. It is a lower spatial resolution, and it tends to be less accurate, partly because of the spatial resolution, particularly over sloped areas such as glaciers and ice sheets. Of course, that's something that folks are interested in the cryosphere. Laser has higher spatial resolution. It's more accurate, but it is affected by clouds in the atmosphere. The clouds will reflect light, just like the clouds block the sun, as well as other atmospheric effects like aerosols and so forth. Now, of course, there is kind of an interesting, if you are interested in clouds, then that's an advantage. If you're interested in measuring cloud heights and things like that, radar doesn't help you very much. You want a laser, but for surface properties, that's an impediment. So the first laser altimeter, first major one, satellite born, was it was ICESat, the Ice Cloud Inland Elevation Satellite. That was launched in 2003. It has the Geoscience Laser Altimeter System Instrument or GLASS. There was 3 lasers on that. They had they had redundancy to try to make sure the mission would last long. But unfortunately, there was an issue with the design of the lasers, and I don't remember all the details, but basically they were burning out essentially or losing power much faster than they had anticipated. So I think laser 1 they turned on, and the plan was to turn it on and let it run, collect data and year round, 24/7. But they lost that laser very quickly, and they realized that was a problem, and so they couldn't just turn on the next one. It would have the same problem. So what they did to try to maximize the mission was you operated them intermittently, operating the second 2 lasers intermittently for roughly 33-day periods. And that got them from 2003 to 2010. So we've got a pretty good time series of missions, but generally 2 or 3 times per year was when they operated these. So they couldn't get the full season, they couldn't get every single day with this mission, but it's still a successful mission. It's a waveform laser system. It's 532 nanometers and 1064, which is green and red. Infrared, yeah, right, sorry. And then so that was followed by ICESat-2. And I want to take this moment to talk about NASA missions and mission planning. There's a lot of stuff that goes into it, a lot of details, the satellite design, orbit design, launch, everything, what the science objectives are. But really, when you get down and start a NASA mission, the most important thing is, first of all, 2 most important things. First of all, you need to have a good acronym. Well, you need money, yeah, but you need to have a good acronym. And ISAT is quite good. You got the land kind of stuck in there. Maybe it should really be ICESat, but still, it's ISAT. It's focused on ice. It's really cool. And then you need a good icon. And ICESat-2 is really cool because it's got the penguin with the number 2. So in my view, this is one of the more successful NASA missions, for no other reason than that.
In terms of marketing.
Yeah, in terms of marketing, yes, it's very good.
Amazing penguin.
Yeah, it's really a cool penguin. Yeah, I don't know who came up with that, but they deserve some sort of prize.
The 2 until you just said, I was like, oh, he's just a cute little mascot, but no, he's also the 2.
Yes, he is also the 2, yeah. So, but it actually has been a really successful mission, as you'll see. It was launched in 2018. Carries what's called ATLAS, the Advanced Topographic Laser Altimetry System. This is a photon counting laser, so that's different than what ISAT was, which is a waveform laser. I'll talk about that in a moment. It's a green laser, and it's just the 1 green laser, but it has 3 beam pairs. So actually 6 beams total. Show that a little bit more in a minute. Strong and weak beams, and it's 10,000 pulses per second, which compared to ISAT had 40 pulses per second. So tremendously larger amount of data and spatial resolution and so forth. It's on a 91-day repeat cycle, so it repeats the same ground tracks every 91 days. And within that 91-day cycle, there are 1,387 individual orbits. So that's one of the ways that they count those. Science objectives, there was 4 science objectives, measuring ice sheets and their effect on sea level, changes in ice sheets, melting of ice sheets, and effects on sea level rise, and changes in mass of ice sheets and glaciers, estimate of sea ice thickness, and then height of vegetation in forests and other ecosystems. Now, the sea ice thickness, I just took this off the ICESat mission page, and I don't know if they updated this or if this is incorrect, because sea ice thickness was not actually one of the mission objectives initially. It's not a standard product. It's freeboard, which is the elevation above the water surface. And the rationale is, or was, that they weren't sure how well they could get thickness, that they could get it good enough. So that was not one of the initial objectives, at least as I remember it. So I don't know if they changed this or if it's just kind of a mistake and they were, not distinguishing too much between thickness and freeboard, or keeping it simple for more of the lay person, non-technical person. But anyway, I'll talk about that more as we go. So waveform versus photon counting. So they both, are sending down a signal and then retrieving it and timing it. A waveform is just sending out basically a pulse, and it has, a peak transmit pulse, and you can see on the right, or even on the left here, it has a peak energy level, it goes down and reflects back, and then you can measure the peak time to return. TOF is time of flight. That signal will get broadened generally as it interacts with the surface and the atmosphere. And so that gives you, basically the time and an indication of what the surface is like. Photon detection, what it's doing is it's sending out individual photons and then measuring the return of those photons and tracking those photons essentially individually. So you get this like photon cloud in the lower right, where you get these raw photons coming in. Each of those little dots is a photon essentially. And so waveform is better for vegetation because you don't lose as many photons through the trees, and you get a more pure signal. I don't know the details of that, but generally you'll get better penetration through with a waveform. Whereas photon counting can give you more precision, and especially when they're weaker signals, because you can get photons. You may get fewer photons, but you still get photons back from those. So comparing ISAT-2 to ISAT, like I said, ISAT is a single beam, 40 hertz. Compared to ISAT-2 is 3 pairs of beams, 10,000 hertz, so much more data. The waveform, you get 60-meter spot basically on the surface, and it's doing that about every 170 meters. So at 40 hertz, 40 pulses per second. So again, it's a waveform laser. The photon pulses at 10,000 hertz is every 0.7 meters. So really, really dense. But one of the things is you send those pulses down, and I'll show this more later, but you don't get near as many back. And to get a signal, you may have to accumulate those over time. So the actual resolution varies depending on the surface and the conditions. But generally is at least as higher than ISAT. And it's a photon counting laser. And this just shows a couple kind of ground tracks with at least the schematic. It's probably not exactly to scale, but it just shows how much more coverage you get out of ISAT-2 compared to ISAT on the left. So like I said, it has 6 beams, it has 3 strong and 3 weak. The weak and strong pairs, it's a pair, they're 90 meters apart. And then the 3 beam pairs are about 3.3 kilometers apart. Having these 3 beams, it's good for detecting slope surfaces. Because if you're on a slope, those beams will register. You can calculate a slope over that 6.5 kilometers or so. Compared to if you have 1 beam, you don't know what the slope is. You just got an elevation. So that's helpful. The weak beams are less accurate. There's less energy. Basically, the 4 and the 1, basically that's just a relative strength. So the strong beams are about 4 times as strong, 4 times as much energy as the weak. But the weak beams are more useful for aerosols, and they can augment, especially low reflective surfaces. And so any additional return energy can potentially be helpful. So when you look at this, you've kind of got to keep track in the data products. There's just data for, at least in a lot of the products, the track products. There's 6 beams, and you have to keep track. But you just look and okay, there's the strong beam, the weak beam, and the strongs on this side, and the weak beams on the other side. It's a little complicated, but you can figure it out. It's no big deal. And you've got it. Once you've got it down, you got it down. Except shoot, they turn the satellite. And so you have to keep in mind which direction the satellite is pointing. They do this because to optimize the sun angle for the solar panels. So there's a sail and an airplane mode, depending on whether it's which way it's pointing. But basically, it turns to make sure it's got the solar panels pointing towards the sun as much as possible. Also does some heat regulation to keep the instruments out of the too much sunlight. So it flips back and forth. This is all in the data products and metadata. But this is something like if you're using the data, you have to keep that in mind and know which orientation it is. If you care about which beams, whether the strong beams are to the right and behind or to the left and front. So this is one of my more favorite figures here. And I don't know who actually came up with this. I grabbed it from somewhere. It's available on the ICESat-2 mission website. I think it might have been Tom Newman, who was the science lead or project scientist for this. But I'm not sure. But this is basically, altimetry in general, but specifically ICESat-2. So you start off with a transmitter, and you're sending out the photons and you're starting the timer. That's the actual timer on the satellite, by the way. There's a little thing that's clicking it. Yeah.
Like I with his thumb.
Yeah. Sends out many trillions of photons. I've seen 20 trillions, I've even seen 200 trillion. I'm not exactly sure. You see different numbers in different places, but it's a lot. So it sends out 20 trillion photons. All these photons start shooting out, clock starts, goes down, hits the atmosphere, there's clouds, there's aerosols, there's other things, just in general, a lot of things get absorbed. Basically less than 80% get through the atmosphere. And that's, again, not counting clouds per se. Like if it's cloudy, none of them get through. But a few of them get through, the green ones. And also, of course, in the daylight, at least, the sun is emitting photons. So you've got all these photons from the sun, many trillions of sun photons there. So goes down, hits the surface. Some of those are going to be absorbed maybe by the surface or scattered out of the field of view, but some of them bounce back towards the satellite, and they come up. Then they come back up towards the center. Now you got to filter out the sunlight ones. You don't want those because those are coming from different places. You want to only get the ones that the transmitter sent out. So there's a filter to do that, and then you come back and you end up on average, and it varies, but on average with 12 photons. So 20 trillion plus down to 12. So this is like very few photons survive to get back. It's a very few lucky ones. But this is, to me, it's really amazing that this instrument can get data. And it's timing it to precision of 800 picoseconds, which is, I think it's 800 trillionths of a second, something like that. Or 0.8 billion of a second or something like that. So lots of zeros there. And it's, measuring the surface down to about a 2 centimeter precision, less than 1 inch, over 310 miles, over a 620 mile round trip. With all this stuff going on, it still manages to measure the surface to within about 2 centimeters. So, yeah,
That's like a crazy attenuation rate. Like,
yeah,
even if it's only 20 and not 200 trillion, that's still so
Yeah.
many that get lost.
I want to know more about that filter box.
yeah. I mean, I think what it's doing is it's checking the wavelength, and it only allows like very specifically 532. I mean, it's still, you would have some sunlight at 532 in
Right.
theory, right?
That was my question.
Yeah. And if you look at the data products, and I'll get into some of these, you do get these photons come through. But what happens is they're more scattered, and you still get a density along whatever your main surface is, and so you can still pick that out. If you were getting all of the photons, then it would really be a mess.
Yeah, okay, that makes sense.
Yeah, but it is, you do get better, or at least it's easier to interpret data at night, because you don't have that problem. So, that's the basics of it. Now, there's a lot of complications, beyond just getting the photons and timing. Because there's a lot of things that affect these, and, first of all, and I'm not gonna go into detail on all these, but all of these have to be accounted for. I mean, first, you need to have precision orbit determination, that's POD, you have to know really precisely where your satellite is, altitude wise, and where it is in the orbit too. So that's done through GPS and other ground-based ranging systems. And so there's a lot of work that goes into making sure you get that orbit as absolutely accurate as you possibly can. Without that, you really, if you don't know where the satellite is, you don't really, you don't have a good sense of, you can't have a good sense of where the surface is. Then it does go through the atmosphere, there's some corrections for that. And then it's, you're hitting the surface. This is for a sea surface, which is actually more complicated, I would say, than the land surface, because the sea surface is in motion. There's tides, there's currents, there's winds that are roughening the ocean and that are raising it up or pushing it down, the atmospheric pressure. So you have your reference ellipsoid, which is basically your reference for your system, for the orbital system. Then you got your geoid, which is the gravitational equipotential, where gravity is. But then you've got all these sea surface, different sea surface levels that account for the things like tides and stuff. So all of that has to be accounted for, at least as well as you can do to again get accurate data. So this is the products, the mission products. These are the standard products are updated. Generally, the aim is within 45 days latency, so 45 days after collection. But they're for a lot of applications, that's not really all that useful. It's just too long of a latency to if you're trying to look at something that needs something more timely. So they did later develop these quick look products for some products, and these are about 3 days. And so that allows these ICESat-2 data to be used in a more applied way for a lot of things. And so you have, ATL0, which is the raw satellite data that comes in, they do some reformatting and conversion, gets you to ATL02. And that's basically like uncorrected photon returns. And then they do the precision orbit determination. There's also pointing determination. You got to make sure you know where you're pointing as well. And then that gives ATL03, which is your geolocated photons. So that's really the base data set. That's the data set that generally users are going to want to start with if they want the most fundamental data. The earlier data is just kind of intermittent or intermediate, getting to something that's usable. It also goes, there's the backscatter profile ATL4, which is actually the atmospheric data. So there's two ways it goes, and one is the ones that get to the surface, those go into ATL03, and then the ones that are in the atmosphere go to ATL04. That's a level 2 product, so these are long track products. Then it goes into the higher level products, which are like the geophysical parameters. I don't know how well you can read that. There's the land ice height, the sea ice height, vegetation height, and then the ATL4 goes into the atmospheric layer characteristics. These are long track products. By the way, the convention, these should really be blue, should really be level 2B products. But they call them level 3A. And for some reason, which I don't really know why, but to me that's kind of confusing, but that's what they did. Level 3B is gridded products. Level 3 generally means gridded products. That's the standard for products. But 3A is not gridded, 3B is gridded. And then these are basically taking those lower level products, the long track products, and then gridding them, which is a more convenient format for a lot of users. It also gives you kind of more of a, whether it be a daily or monthly, a seasonal average, and it kind of accumulates those in a smaller smaller size and easier to work with for a lot of users. Okay, So along with those standard mission products, there were several of those, as you saw. There are what are called related products. So these are not standard mission products that came out of the original mission planning, or there were some that were added afterwards, like the quick looks. But there are other products that came out of whether it be the project science office or even just like research products. So one of those is sea ice thickness, which I talked about earlier. So there is sea ice thickness products, sea ice melt pond characteristics, boreal biomass density, Arctic ice shelf grounding zone. Those are kind of the main categories. This is just an example of the melt pond detection. This is just along the track, along sea ice. The green, well, the colored line is basically like the surface. And you can kind of see it bouncing along, there's little ridges. And then in the middle here, my arrow comes through, you see this kind of like dip where there's, it's not maybe quite as well defined, but it's, you know, there's definitely something there, right? That little U shape. And that's a melt pond. And what's happening there is the photons, some of the photons are hitting the water surface and reflecting back. So you get this nice little straight line there, the level water surface here. But some of them penetrate through and hit the bottom of the melt pond. These are pools of water from meltwater on the sea ice. And so this is, you know, really pretty cool. This is not something that was originally planned. I don't think they really were sure if this could be feasible, you know, what would happen with these. But, you know, visible light can penetrate down through the surface. You know, if you swim underwater, you look up, you can see light. So it's the same kind of thing. But it's just a matter of how much energy there is in the photons and how deep the photons can penetrate. So that's kind of that's a little foreshadowing for later on. So sea ice, I'm gonna go into a little more detail, just because personally, I think, you know, sea ice is just a lot more interesting and a lot more important than these other parameters. But no, it's actually because I know a little bit more about these, and I don't have time to go into details on all of those. So I'll show some of many of them, but sea ice is a particular challenge. One, because it's thin. You know, sea ice is a couple 3 meters thick, and what you're actually measuring with the laser, you know, you're measuring the part above the sea surface, so that's only about 10%. So if it's 2 meters, you're measuring about 20 centimeters. So, so that's a challenge in terms of the accuracy. The other thing is there's snow on top of the sea ice. So the laser reflects right off the top of the snow. We're pretty close to the top of the snow. So the freeboard, oftentimes when we think of sea ice freeboard, we think of the ice freeboard, the level of the ice surface above the water line. But the laser freeboard you get from ICESat-2 is actually the snow and ice freeboard. That's the total, that's what the laser is measuring. It's measuring from the height of the snow. Now radar, like from Cryosat-2, actually penetrates through the snow cover. At least that's the assumption, and generally that's true. So it's actually getting the sea ice surface through the snow cover. But when you know these, you know the densities, which there's some assumptions that have to be made, and certainly some uncertainty, especially with snow density, you can get thickness if you know that. This is the two sea ice freeboard products before I get to the thickness. ATL7 is sea ice height, ATL10 and 20. ATL10 is the on track freeboard, and ATL20 is the grid freeboard. There's a lot of stuff that goes into calculating these, and basically, you know, the height is just basically aggregating geolocated photons. You can't really get for any individual photon because there's just too much noise and too much uncertainty. So you have to accumulate a number of photons to get enough signal over the noise. So what was determined was 150 photons. So depending where you're at, you know, how long does it take you to get 150 photons returned? So the spatial resolution varies, and but then you can get the sea ice height. It's limited where sea ice concentrations is at least 50%, and you're not too close to land, more than 25 kilometers of land. So that gives you just a raw height. For freeboard, you want to know what the height is relative to the ocean. And so what's done there is they calibrate, quote unquote, calibrate the sea level by looking for leads, which are the open water areas in the ice. And then they say, okay, that's the open water, and then everything else is adjusted to that. But you can't just do that like once per orbit or anything. You need to have that relatively close. So they look for within 10-kilometer long track sections. There's also further complications because the leads can vary in how they reflect the photons. They can be dark leads where they kind of absorb most of it. You don't get much signal. There can be kind of specular leads where you get a really bright return, depending on the angle. So there's all these. This is kind of like a decision tree that helps decide, okay, what kind of surface are we looking at? And then that helps inform or does inform the algorithm on how to calculate the freeboard. This is just an example. You can kind of see, this is just overlaid on SAR images. It's really pretty cool. Like if you have these pretty coincident, you can really see the dark areas of the leads, and that's where it's flat and low. So that's where the open water is. And then you've got just a plot of the photon returns, and it also gives you the segment length in the blue there. And so you can see how long, it gives you a sense of what the actual resolution is. So thickness, you have to account for the snow because we need to, take care of the snow. So this is, if it were up to me, this is the way I would take care of the snow. Just get rid of it, just plow it off, and then we have to have nice bare ice and we don't have to worry about it. But alas, you can't really do that over the sea ice. So in order to correct for this, there's a couple of ways that I'll mention here. First, one is to use a climatology. There's Steve Warren, whose papers, one of the more well-cited papers, basically took a lot of data from Russian drifting stations over about 40 years and compiled that into a climatology. That was mostly on multi-year ice. It was realized, especially in the newer environment in the Arctic, that there's more first-year ice. And using aircraft data, they basically came up with a simple rule: first-year ice has about half the snow of multi-year ice. So they then adjusted this Warren climatology for ice type. So that's kind of what's been used for the climatology. The other way to do it is use atmospheric reanalyses. This is the model and data integrated. You can measure how much snow falls, and then it, however much snow falls, it's accumulated on the ground, and that's your snow depth. And there's like 3 different ones: the NESO-SIM, NASA Olarian Snow on Sea Ice model, Alec Petty. That's the one that's used for the standard products here. But there are a couple others. The snow model LG is actually also archived at NSIDC at the DAC. That does a little bit extra in that it does a Lagrangian, and it also uses a snow model for the winds to blow the snow, and then it vectors the parcels of ice and snow. But the NESO-SIM is the one that's kind of been the standard. So sea ice thickness. There are 3 different products. It uses the NESO-SIM snow like I talked about. There's a long track thickness, there's a monthly gridded product, and then there's a seasonal 3-month gridded product. And Alec sent me this last week or a couple weeks ago. So this is like hot off the presses data, and this is ATL10 version 7. This is the freeboard. So this is published, but this gives you the freeboard, and this is for the entire winter season in the Arctic, 2019, November to April 2019, and then the subsequent years, with the latest year through April 2025 in the large figure. You can see, there's the thicker freeboard is towards the Greenland and Canadian Archipelago, which is kind of what we normally see. And then it returns the snow depth from NESO-SIM. So you have the snow depth. Again, the snow tends to pile up more on the multi-year ice, the first-year ice. And you take those 2 together and you get the thickness. And so this is the thickness. And then you can do an anomaly. This is an anomaly relative to the entire record. So it's just showing you relative to, where it's relatively thicker or thinner. You can see a lot of variability from year to year in terms of that. And so it's kind of interesting to see the problems. It's only, 7 years, so it's you can't really call it a climate record. People have started looking at this with other things to get a longer term record. This is just the trend monthly data for the different years and different colors, the black being the most recent. I think kind of interesting, the thickness this last year has been thinnest or among, or very close to thinnest in the late winter of 2025, February, March, and April. So it was a relatively thin year. All right, another way you can do this is, as I mentioned earlier, radar penetrates through the snow to the snow ice interface. The laser reflects off the top of the snow surface. So it's like, well, why don't you just take the two of them and you've got, the top of the snow and then the bottom of the snow, and you just subtract them, and that's your snow depth. So then you got your snow depth, then you get your thickness, and you're done. Like, why hadn't anyone thought of this before? Well, there's a lot of challenges. ICESat-2, different spatial resolution than ICESat-2, so you gotta consider that. There is some uncertainty in the radar penetration depth. There's uncertainty in the densities. You need to know that even if you have the heights measured well, you need to know the densities. And then a big one is the different sampling time, is that they're in different orbits. They might be many, many hours different, and when you see one to the other, and things can change, the ice moves. But one solution to that was what's called cryo to ice. And that was basically a European project to adjust the ICESat-2 orbit. They kind of, ICESat-2 has been going for 15 years. They collected all their primary objectives by that point. So they thought, well, we can adjust the orbit so that it's not the same orbit as ICESat-2, but there's a lot more crossovers that are near coincident in time. And so you can have much better agreement. And this has actually been done. Sarah Cassimi at JPL, and along with Ron Kwok, who has since retired, but they went through, this is a lot of data here, so don't worry, but basically the snow depth is on the left, which is taking the difference between those two, and then putting that snow depth into the relevant density formulas. You can get the ice thickness from ISAT-2 or CryoSat-2. And so this is a product that has been delivered to NSA. This is a research product. And so it actually looks pretty reasonable. So it's quite nice that this worked. And then just as an example of carrying this on, they connected this with CryoSat-2 and ISAT. So you have a longer term record there from all the altimeters, all the polar altimeters. And you can see the pretty stark decline in the thickness. Well, this is actually volume, so thickness times the concentration. Yeah. So I know I'm running. Well, I got a few more. Okay. So that was the sea ice. So that was a lot of detail there. I'm going to do a lot less detail for these others, but I just wanted to point out, that there are these other products. Ice sheets is one of the main ones. This is ice sheet height change from 2020 to 2024. This is ATL 15 product, which is a monthly gridded product. And so it shows the changes. You can see, like, this is the Thwaites, Thwaites and Pine Island areas here. I forget which is which now. But along the coastline, there's, really sharp. This is the change in elevation meters per year. And so, half a meter plus per year in these areas over like 4 years. So that's a couple meters. And you do see areas where it's increased in the blue there. That's been noted in the data in the recent years that the steep decline in Antarctica has kind of slowed at least a bit, at least in some areas, and the overall average. And a lot of that's has to do with more snowfall. It's not that it's, global warming has stopped or things have stopped melting, but in certain areas, there's a lot more snow that's accumulating in the winter season. So even if it melts a lot in the summer, you still are gaining mass in some areas. But along again the Pine Island Lakes area here, and then along the Canadian or along the Antarctic Peninsula, there's areas that are losing ice. And this is actually the ice shelf, the Larsen ice shelf here. And in Greenland, you don't see, maybe a little bit in the higher elevations, again, maybe due to increased snowfall, but all around the perimeter, pretty much, all the kind of the draining glaciers, you've seen reduced elevation, reduced mass. So vegetation, again, you're measuring the height of the the elevation and as well as the canopy height. This is using open altimetry, so I just pulled this up this morning, just for how to do it. Open altimetry is a really great tool for looking at ISAT data, ISAT-2 data and ISAT data. And so I just wanted to highlight this. You can go in, look at the ground tracks and then zoom in on an area and actually look at, it pops up the data. So the top is the elevation, the surface elevation, and then the canopy height below it. Yeah, I picked that area in Western Michigan near my sister's house. It's not right over, I maybe could try to do it right over, but I picked an area that was a little more forested, so, but. So, you know, again, in terms of the canopy height, you're getting returns from photons at various levels. If you think of a, you know, your typical forest, it may bounce off the very top of the canopy, it may penetrate through, there may be gaps, and then some aren't gonna get through to the surface. So you end up with something that looks like this. This is like your photon cloud with the ATL-08, that's the vegetation canopy classifications. And so the red is the ground, and then the blue is within the canopy, and then the green is the canopy top. So you can almost like visualize the structure of the vegetation of the forest there. And this is a relatively new product, which is but vegetation biomass. So it's basically using the vegetation canopy height, and then as you bring in other data, like what kind of vegetation is it, and other ancillary data to actually measure the biomass. So that's kind of a neat product. I show that here. And again, that's archived at the DAC here. A quick one more altimeter to mention in the context of vegetation is JEDI, Global Ecosystem Dynamics Investigation. This is another one that's, you know, they did a really nice job of coming up with an acronym, JEDI. You can't be cooler than JEDI. Focuses on the forest, and it's on the space station, so it's not a polar orbiting, so you don't get the polar. It's also a full waveform LiDAR, so that's different than the ICESat-2, but there's the potential to combine those. There's one combined product there. There may be others, but the one that I found. So and JEDI, it's still operating. It did have and at the time where it went out of operation for a while, but they were able to get it back up. So that was what was called the return of the JEDI. So another one, bathymetry. So I showed earlier melt ponds on sea ice, and it's like, oh yeah, you know, cool. We can actually see the bottom of a melt pond. Well, can you see the bottom of the ocean? And this was something that it wasn't part of the standard mission products. It's not a mission objective, as I mentioned, but looking at the data, looking at the photons, could very clearly see photons penetrating through the water surface. And you know, how far can they go? Well, at least for shallow areas, such as along the coast, they reach the bottom. You can get a very clear bottom signal. And so you can do coastal bathymetry. And this is really helpful because coastal areas are not always well sampled by other methods. You know, if there's shallow areas, you can't send in a ship with a depth sounder very easily and really map these out. So this product ATL-24 was developed not as part of the original mission, but now it is a standard mission product. And this is just an example that I found that it kind of shows the value of the product or the potential value of the product. This is near Flamenco Beach, Puerto Rico. So that's the map. I didn't check exactly where along Puerto Rico it is, but it's in a kind of a shallowish bay, and the ship got grounded there. And you know, they didn't have the bathymetry to know exactly where they should go. And what happened? This is the sea level surface here in the kind of the teal, that straight line, and then the blue and white is the bathymetry. That's the corner, you know, the bottom of bottom of the ocean essentially there, or bottom of the bay. You go down and you can see right here, you know, it's kind of going down. So if you're a ship, you're like, oh, okay, we're good here. And then all of a sudden, boom, there's like this shallow area, only I think that's meters. And so if you have a ship with a keel or a deep draft, it's gonna hit that. So that's you know, just a nice example of how this data can be useful. All right, so I'm gonna finish up with some fun stuff. this was the thing that the science team did, the ICESat-2 science team did, look for kind of fun features. They would even have a little competition for these. And so, thanks Lisa for passing these along to me again. So I picked out just a couple. This is the Pyramid of Menkaure in Egypt, and Al Ivanov, who's at NASA Goddard. There was a couple tracks that went basically right over this small pyramid, see right here. And so, oops, yeah, so you can see the elevation there as it goes over the pyramid. Another one that's fun, Kelly Brunt, who's now at NSF, but she was at NASA Goddard and was part of the team for several years. A track that went over the Bellagio. And the Bellagio has this big fountain out front, if folks are familiar with that, if you've been to Vegas. Or it's also well known from the end of the Ocean's 11 film, where they all come out and stand in front of the fountain and it shoots off these, oh yeah, that's the Ocean's 11 film there. So it's a really big fountain, a lot of water, and it's, you know, it's not super deep, but you can actually detect the fountain, this top where the arrow is pointing here, that's basically the fountain, the water surface of the fountain. And then these bottom returns are basically the bottom of the fountain, and there's, you know, some infrastructure, and there's some things are higher than others, that you can kind of see in the picture there. So that's kind of a fun little thing there. And then another one from Al Ivanov, Machu Picchu, tracked across Machu Picchu, maybe a little hard to see here, but there are these little dots that where the track went, where the photons went. And you can see on the upper left here, this is kind of coming down this mountain that's the famous scene from Machu Picchu, and then going down, and kind of like, this is kind of like the relative bottom here, which is basically like right in this area here. So I think there's one more, is the Arecibo Observatory, the big dish in Puerto Rico, which collapsed in 2020, and the track that went over that, this was, I forgot to put that, I think this was 2023. Oh yeah, there it is, 2023, I just put it in. And you can see this big dip where basically you have this big hole in the ground where the satellite, where the antenna dish was suspended before the cables broke and it collapsed. Almost done here. Okay. So status currently, and kind of knock on wood, you know, hopefully these things can be working, but so far been working nominally over 7 years of operation. We're in cycle 29 now, I believe, so in these 91-day cycles. And it was originally planned for like a 3-year mission. It's standard satellite. I think maybe it was 5 they were aiming for, but we've exceeded that. It's operating nominally. The laser energy is still good. It's got enough fuel to last, as my memory recalls, it's like early 2030s. And so, yeah, we've got, all systems keep working. We've got plenty of more data to collect, which is really nice. The shot count as of this morning, that's 2 trillion. Recently went over 2 trillion shots. That's now over 2.2 trillion. Yeah, I was gonna try to update this before this meeting, but you know, trying to keep track of it's kind of hard. In terms of data, 45, over 4,500 registered users, over 60 million files downloaded. So it's, you know, really been a very widely used product. The top products, this is by downloaded files. If you go by users, the order changes a little bit, but it's still, these are still the top 3 by far. The ice sheet elevation, vegetation canopy height, and the geolocated photons. So that's it. And yeah, maybe the next one.